Okay, so here's where we were last time. We were talking about Fibonacci numbers. This is just a quickie application of the idea of diagonalizability. So this is not really the point. This is not why we did all that diagonalizability stuff. But it's just that our real applications go a little bit into the future, right? We're going to have to wait until Chapter 6. We got a bunch of stuff we have to do before then. So I wanted to give you a little something to whet your appetite. So this nth Fibonacci number business. What we saw last time is that this Fibonacci sequence, right, defined by this relation, could alternatively be described by this matrix relation. If you just, so in some sense, multiply out the two entries there in the product, they are basically the same as the relation. Okay. So why would I care about such a thing? I've successfully taken a simple formula and turned it into one that's more complicated. Why is that a win? Here it comes. So the idea is to realize that if this matrix effectively moves you over one spot in consecutive pairs, like it turns that consecutive pair into the next, you might say, consecutive pair, then alternatively, you could think of this as that you start with the first consecutive pair and that you get to the, depending on what you want to call it, maybe the nth consecutive pair, n plus 1th consecutive pair, by doing this matrix in different times. So that matrix, just repeat. So what does that buy us? How does that help us find a formula for the Fibonacci numbers? Notice that what we are looking for is the bottom entry in that little vector. That vector being this product being from 1, 0. We're looking at the left column of that A to the n matrix. So we are looking for the bottom left entry in a high power of a matrix. And on the previous page, one of the very last things we did last time, we now know how to raise a matrix to a high power. Diagonalize. Capitalize on the fact that diagonal matrices are super easy to raise to a high power. So there's a bunch of details in this that I'm going to largely leave to you guys, but here's the punchline. That matrix, this matrix that sort of does the Fibonacci relation for you, there's the eigenvalues and eigenvectors. I have them written in terms of the golden ratio there, G, what I'm calling G. I want you all to go through that process, confirm that these are the eigenvalues, these are the eigenvectors. You are going to have to play with a little wacky algebra of the golden ratio. The golden ratio has the feature that its reciprocal is itself minus 1, and that causes all sorts of other odd things to be true. If I remember correctly, G squared is G squared is G plus 1, I think, or something like that. So you got to play with it a little bit. But anyway, having done so, these are the eigenvalues and eigenvectors. The eigenvalues, the eigenvectors, you'll notice, are the columns in this conjugation. The eigenvalues, you'll notice, are the diagonal entries here. And then raising A to a high power is done, in effect, by raising the diagonal to a high power, which is easy. Okay, last quick observation in terms of simplifying this. Notice that this eigenvalue is smaller than 1, and so if, in some sense the whole purpose of doing something like this is to compute really far down the list of Fibonacci numbers. So we don't really need this formula when n is 5, right? That's an easy one. But if n is 100 trillion, that's where we're in trouble and we really need this formula. Well, if n is 100 trillion, this number being less than 1 in magnitude, this term's going to go away pretty much to a very close approximation. That is approximately 0. And so at this point, it's really easy to multiply this whole thing out. You just multiply these matrices. Right? It's real easy to do. Just a couple of details. As previously discussed, we want the bottom left entry, and that bottom left entry is that. And check it out. Give it a try. right? You could program a little computer program that just check that this works actually for the first so many different values of n, and then you have an instant formula for how to compute Fibonacci numbers. By the way, notice in this approximation, the approximating sequence here is geometric. So Fibonacci sequence is approximately geometric. Okay. All right, this next example, I'm going to be super quick. This was not actually intended to be an example. This was intended to be a template of possibly any number of different examples. So the observation here to make is that when you're describing a system, sometimes that system is described by a collection of parameters, A and B, let's say, and the system might take values, say A and B, not sort of continuously over time, but it might take values in stages, right? So instead of A being a function of time and B being a function of time, you might have A is a sequence and B is a sequence, like I've got described up there. So if that's the case, if A and B come in sequences like that, look for the possibility that either as written there will be a matrix relationship between them. Probably not, right? But or that you might be able to take these variables and by shifting them or taking logs or whatever manipulations you might be able to do algebraically with them, you might be able to create sort of alternative variables that are related by a matrix relationship. And this is not at all unreasonable. This comes up. Right? So the point is, when you have done this, notice that predicting the future state of the system comes down to taking the initial state of the system and figuring out how to multiply that by m to a high power. And, raising a matrix to a high power, same deal, right? It boils down to, once you found the eigenvectors and eigenvalues, of just raising the diagonal to a high power. So the observation on this page is just that this, raising a matrix to a high power could have any number of different applications whenever you can relate a system by a matrix. Okay, so moving along. So here's a new topic to talk about. It's called Jordan canonical form. First, I want to tell you where this comes from. It comes from asking this sad question right here. What if our matrix is not diagonalizable? And remember, this happens, right? I mean, we know what the rule is for whether a matrix is diagonalizable. We talked about this last time. We proved it like 3 different ways. A matrix is diagonalizable if there's no missing eigenvector. For every eigenvalue, you get exactly as many eigenvectors as the multiplicity sort of makes you want to get. In other words, that you have exactly n eigenvectors, that you can make a basis out of your complete list of eigenvectors. If that's the case, then it's diagonalizable. And if it's not the case, if there's a missing eigenvector for any eigenvalue, you're too short of eigenvectors. You don't have enough eigenvectors. You cannot make a basis, and your matrix is not diagonalizable. And this is bad news. Okay, so what we're going to consider here is, then what do you do? I mean, diagonal is great. It's really nice to have a diagonal matrix. We're going to see powerful applications in Chapter 6. We already saw some kind of cute applications in the last few examples I just did. But what do you do if the matrix is not diagonalizable? And the answer is, good news, okay news, is that even if it's not diagonalizable, you can always put a matrix into Jordan canonical form. Always. So, good news is that this is something that always works, and that's a sigh of relief. This is never not on the table, right? That's nice. The bad news is Jordan canonical form is not as nice as diagonal form. It's really not. It's weird in certain ways. And it's a long story for me to tell you what Jordan canonical form is, so, bear with me. We're going to have to go through and describe all of that. But as we go through and describe what Jordan form is, Jordan canonical form, don't forget what we're doing here. We're talking about in our attempt to diagonalize. We're talking about the story where what we're interested in is the underlying linear transformation. We're not row reducing. I don't care about homogeneous solutions. That's just not the kind of question we're interested in. We're interested in an underlying linear transformation. We're interested in things that preserve that underlying linear transformation. So by way of change of basis, aka conjugation similarity, we want to understand that linear transformation. So when I say we can put it into Jordan form, I mean by way of conjugations, change of basis, similarity. Okay. So with that context, here's the long list of rules. I'm going to start by telling you about something called the Eigenvalue Block structure. This is what I call it anyway. Let's get this all on the page. Here's your Jordan canonical form. Inside of the Jordan canonical form, there are blocks, square blocks, on the diagonal. By on the diagonal, I mean that the appropriate corners are exactly on the diagonal. And everything outside of the diagonal is all zeros. So all zeros out there, all zeros out there. This is good news. We like zeros. Zeros represent things we don't have to worry about. Very nice. Okay. Now, it turns out that there's some things that I can tell you about an eigenvalue block. This is as it turns out, eigenvalue blocks relate closely to eigenvalues as follows. You look at the corresponding factor. The eigenvalue that you see from that factor is the diagonal entry in the corresponding eigenvalue block. Just how it turns out. The multiplicity of the eigenvalue will tell you sort of the, I did it over here. Will tell you the size, the dimension, if you will, of the eigenvalue block. There's a strong relationship there. So this is why I like to call these eigenvalue blocks. These blocks are so closely connected to the eigenvalues. Side note, the book does not give a name to these eigenvalue blocks. I think they deserve a name because of this close relationship, the close relationship to eigenvalues, thus the name Eigenvalue Block. Okay. All right. Okay. So next question, what's inside of an eigenvalue block? Can these just be any numbers at all, or what's the rule? There are more rules for what is inside of the eigenvalue block. By the way, then there's rules for what's inside of that. We're going to be doing kind of a chemistry, if you will, sort of Jordan canonical form. Remember, in chemistry, you have molecules. Yeah, but inside of molecules, there are atoms. Inside of atoms, there are protons and neutrons and stuff, right? So we're going to be looking at the large-scale structure, and then a sort of a medium-scale structure, and then a smaller scale structure. Unlike with chemistry, it ends after 3 structures here. Okay, so here's our eigenvalue block. And let's talk about what's inside that eigenvalue block. So here it is again. There's that eigenvalue block. Inside of an eigenvalue block are things called basic Jordan blocks. More blocks. Also square, also on the diagonal. And just like with the eigenvalue blocks, remember outside of the eigenvalue blocks is all zeros. Well, likewise, inside of the eigenvalue blocks, but outside of the basic Jordan blocks, all zeros. So lots of zeros. Again, we like zeros. Okay. Now, how many basic Jordan blocks are there? What does that have to do with the eigenvalues? What does that have to do with the eigenvectors? It's a little harder to say. We're going to talk about that a little bit later. How big are these eigenvalue blocks? What dimension are they? That's actually a really hard question. That's something that we're not going to talk about in Math 216. But right now, all we're going to say is that there are basic Jordan blocks inside of the eigenvalue blocks. All right. Okay, next question. What's inside of a basic Jordan block? Here's a basic Jordan block. And the answer is, it's always the same. By the way, let me go back over here. Don't forget, inside of an eigenvalue block, right? We already know that on the diagonal is the eigenvalue inside of every eigenvalue block. Well, therefore, that's the case also for the basic Jordan blocks, which are on the diagonal as well, right? So on the diagonal, eigenvalues sort of has to be the case. They're mostly zeros everywhere else inside of a basic Jordan block. The only other non-zero entries are these ones just above the diagonal. All zeros everywhere else. All zeros below the diagonal. All zeros above, just above the diagonal. This sort of, this sort of parallels the diagonal by one. Okay. So there's our three structures. There's an eigenvalue block structure. Inside of the eigenvalue blocks are basic Jordan blocks. Inside of the basic Jordan blocks, it always looks like this. So those are the rules. Any matrix satisfying those rules is in Jordan form. Now, and there's more to say about the structure of Jordan form. It's going to take us a while to get through all this stuff. Okay. All right, first some examples. Let's get our hands dirty. Here we go. Okay, let's look at this matrix here. Claim this matrix is in Jordan form. Here's how you can see it. That is an eigenvalue block. Notice all the same value, all the same eigenvalue on the diagonal. Okay. Whoops. Okay. Oh, whoops. That's one. Okay, here we go. Here's another eigenvalue block. Down there like that. Eigenvalue along the diagonal. Okay. So what we know about this, the original matrix for which this is the Jordan form, the eigenvalues of the original matrix are 3 and 5. You can see them right there on the diagonals of the Jordan form. And the eigenvalue of 3 has multiplicity 3 because it's a 3 by 3 eigenvalue block. The eigenvalue of 5 has a multiplicity of 2 because it's a 2 by 2 eigenvalue block. Okay. All right, now where are the basic Jordan blocks inside of here? Well, remember the rule is basic Jordan blocks have ones just above the diagonal, like that, right? So this is a basic Jordan block. Okay, now there's a temptation. Sometimes students want to say, okay, well, yeah, but I'd like to do it like this because there's a one just above the diagonal, and what's wrong with that? This is actually not a problem here. There are no entries above the diagonal. So what we call vacuously, all of the above diagonal entries are 1. There are no above diagonal entries, therefore no problem. So that's fine as well. The problem with this, the reason you can't do this arrangement is because this breaks a different rule. One of the other rules is that it's got to be all zeros outside of the basic Jordan blocks, and that isn't. So because of that one there, this is not a Jordan arrangement. What I've got drawn here, that just does not work. So the only way to write a basic Jordan block structure inside of this eigenvalue block is like that. Analogously over here, like that, like that. Everybody on board? Yeah.
Why isn't that 0 in the green box 1 if that's a eigenblock?
Oh, so this is an eigenvalue block. This thing here is an eigenvalue block. It's in basic Jordan blocks that you have to have ones above the diagonal. So the basic Jordan block has that rule. This is an eigenvalue block, does not have that rule. Yeah. Right. Okay. Next example. Not terribly different. Eigenvalue block. Eigenvalue block. Basic Jordan blocks. Well, be careful with this. You can't do this because that does not have ones exclusively above the diagonal. That's not satisfying the rules. You can't do that. You can and must do this. And then down here, that. Yeah? Okay. Lastly, move quickly through these because these are pretty repetitive. There you go. Those are eigenvalue blocks, and the basic Jordan blocks have to be that and that because of that 0, and then have to be that and that down there. Okay. All right, so these are all in Jordan canonical form. All right. Okay. Don't forget what we were doing. We were trying to diagonalize. How do you diagonalize? The whole point of diagonalizing, we're trying to understand a linear transformation. That means we're doing change of basis because it doesn't change the underlying linear transformation. So we're talking about change of basis, similarity, conjugation, however you want to say it. And just because we failed to actually get a diagonal form doesn't change what we were in fact trying to do. Jordan form is still about trying to understand the linear transformation by way of a change of basis, aka a conjugation, right? So it remains that the Jordan form and the original matrix relate to each other by conjugations. And, well, which of these conjugations is it? Well, it depends on which way you're going. Don't forget, think in terms of bases to figure out, which way you're going. We'll talk about that more in a second. Change of basis for linear transformations, recall, works by conjugating by a change of basis matrix, right? A is in S language. J is in V language. So P is a change of basis matrix from V to S. Okay. All right. Further, don't forget a change of basis matrix, the input basis is what the columns are. Right. Well, okay, now to be precise, the columns are the input basis vectors written in the language of the output basis. Here the output basis, the standard basis. So casually speaking, we say the columns are the input basis vectors, B. Okay. That's the basis that we're using to understand T in the form of J. Okay. So because this basis is the basis that we're using to, if you might want to say, Jordanize the matrix, I call this basis the Jordan or a Jordan basis. Quick observation. Jordan bases are not unique. There can be many of them. So we'll call this a Jordan basis. Or you might say this is the Jordan basis that we are using in this case, but there are other Jordan bases. Okay. All right. Notice how similar, oh gosh, I did it. I'm not doing that on purpose. Notice how analogous these equations are to what we wrote down when we were talking about diagonalization. Right? Very analogous. So here's the only thing that's different. When we were diagonalizing, this was a D instead of a J. This was a D instead of a J. D instead of a J. And the basis that we used was made up of eigenvectors. Right? And this is practically character for character the first half of a page back earlier in 5.5 when we were doing diagonalization. This is our summary page for diagonalization. So same story, change of basis, conjugation, change of basis matrix. The columns are the basis that achieves this. It's all pretty much the same. Along these lines, since it's really kind of the same thing, except now we're getting a Jordan form, I call this a Jordan basis. The book doesn't use that term. I feel like it deserves to have a name. Again, it's an important thing. It needs to have a name. I think Jordan basis is reasonable because this is the basis that Jordanizes the matrix. Okay. Real quick. Same deal with which one's P and which one's P inverse? Please don't memorize. Well, please don't only memorize the answer to that question. It's really easy to get it backwards. Remember your P matrix. Maybe P is change of basis from V to S, but there's no law that says that the change of basis matrix as you might encounter it actually will be this thing. Hey, maybe, who knows, maybe it's from S to V or something. Right? That could happen. So if you memorize, you're going to be wrong often because the way these things come at you is not always uniform. Okay, what is always the case, and will always resolve these questions for you, is that if you write A as, well, look, what is this describing with respect to what basis? Write J as describing the same transformation with respect to a different basis. Remember that this basis has to be the same as that basis. This basis has to be the same as that basis. This has to be the same as that. This has to be the same as that. Right? Then you can read straight off of this what that matrix is. That's got to be S to V. There it is. Right? This has to be V to S, which is therefore P in the way that we have things set up for this question. Okay. And therefore the other one's got to be the P inverse, right? This one is P inverse. So this sort of approach will always resolve this confusion, and it's very reliable and not that hard to write down. So please make sure to think in these terms in addition to whatever you might memorize. Again, if you want to memorize just because it's going to come up a lot, which way it goes in these two cases, I suppose that's fine. Right. Okay. Let me pause real quick for questions. How are we doing? Any questions? All right. So next thing we're going to talk about, there's a reason that we care about the following, and that is rearranging blocks. Why we are going to care about rearranging blocks inside of a Jordan form is it's going to take until the next page. So bear with me. It has to do with the question of, is Jordan form unique? That'd be nice, right? Reduced echelon form is unique. That's really nice. It would be nice to know if Jordan form is unique. The answer to that question, I can't even state the answer to that question without going through a discussion of rearrangement. So bear with me here. By the way, there is a homework exercise that is going to ask you to go through a computational process very, very much like what I'm about to show you here. So I think you'll find this very convenient when you get to it. It's one of the AHPs. I forget which one, but one of the AHPs is going to be kind of analogous to this. Okay, so here's what I claim. If you take the basic Jordan blocks sitting inside of a Jordan form, there are certain ways that you could take those blocks and just kind of rearrange the blocks. I mean, you could literally, move this one over here, move that one over there, move this one over there, whatever. Shuffle those blocks around in whatever way. The result would also be in Jordan form. And the question I want to address here is, what is really going on there? What does it mean to shuffle blocks? Is that in any way natural? And if so, how? So it turns out that it is. It turns out that rearranging blocks can be accomplished by reordering the basis vectors. And here we go. A bunch of little details to keep track of here. But let's suppose that I've got a matrix and I put it into Jordan form using that basis. And let's suppose that our result looks like that. I claim, we're going to go through all the details in just a moment. I claim that if I just shuffle those basis vectors, notice, same vectors, still V1, V2, V3, V4, V5, just a different order, V4, V5, V3, V1, V2. Simply reordering the basis vectors, doing the change of basis, writing T with respect to that new reordered basis, you will get that. And notice that this is one of those rearrangements. I have rearranged the blocks. It's the same 3 blocks. Just this one was down there, now it's up here. This one had been up there, now it's down here. We just moved the blocks around. So reordering basis vectors in this case has rearranged blocks. Okay. Now, let me be a little bit more precise, and I like using the colors for this. Let's look at this first block. This first block intersects those first 2 columns. Columns tell you about images of basis vectors. Therefore, these 2 columns are telling you about those 2 basis vectors. I'm going to say it like this. That block corresponds to those 2 basis vectors. Likewise, this block corresponds to that basis vector. This block corresponds to these 2 basis vectors. Okay. Now, notice what I've done. This specific, I made a very careful choice here of exactly how to reorder these basis vectors. Notice the 2 blue ones stay together. The 2 yellow ones stay together. Right? I've reordered the partitioned bases. Right? But the V4 and the V5 stay together, and they stay in that order. That's important. And then notice that the blocks got rearranged in exactly the same way as it has turned out here. Now, I still owe you an explanation of exactly why that is. Details to follow, but how you rearrange the basis, the blocks rearrange accordingly, and still stay looking exactly the same. This blue block here looks just like that blue block there. Okay, now I'm going to try to persuade you that this is in fact what happens, namely that if you reorder as indicated, I'm going to try to persuade you that this is actually the right matrix. This is the matrix with respect to W. There's different ways that you can see this conclusion. One way you can do it is you can actually write down the change of basis matrix. V and W are they're really close to the same base. It's all the same vectors, just in a different order. So this change of basis matrix is mostly zeros with the occasional 1. There's a 1 in every column. Right? So you can write down exactly what that change of basis matrix is and then conjugate, and you'll find that you get exactly what we had above. What I'm going to do for you is start you off on this. We're going to interpret these matrices as representing some equations and just observe that these, in fact, are writing down exactly the same equations. So let's do that just to get something down on paper. Let's look at this column here. Claim that column is an equation, kind of. This column is telling me a certain piece of information. Our rule: columns tell you images of basis vectors. Specifically, that column is then telling you the image of the appropriate basis vector in here. We apply the linear transformation and we write the result in that language. So what we have, this being the 5th column, this is telling us about the image of V5. Furthermore, I can tell you exactly what it's telling me about T of V5. It's telling me that those coefficients are 1 and 6. 1 times that one, 6 times that one. So I have 1 V4 plus 6 V5. So that's what that column says, that equation right there. Is everybody on board? By the way, what we've done here is this is a straight out of section 5.3 columns. If you know what the bases are, columns are telling you about the images of the basis vectors in the appropriate language. Okay. All right, now, that's one of the equations that comes out of here. Let's now instead look at this equation. That column down here in this next matrix. This is the second column. Up there, we were looking at the 5th column. This is the second column. Seems like it's going to tell us different stuff. Look at the numbers inside of this column. They're, it is a 1 and a 6, right? But it's a 1 and a 6 at the very top. There it was a 1 and a 6 down at the very bottom. It doesn't look like this is telling us the same thing, but it actually is. This, being the second column, is telling us about the image of the second W basis vector, which is again V5. This is telling us T of V5. Yeah. These numbers, 1 and 6, those being the first two numbers in that column, everything else being 0. Those are the coefficients of the first two vectors in the output basis. So again, this column, it looks totally different. It's in a totally different location. It is again telling us 1 V4 plus 6 V5. Everybody on board? Now, that's just one of the 5 columns. Exercise I want to leave for y'all. Finish the rest of these. In other words, write down all the 5 equations, all the 5 images that are being told to you by that top matrix. Write out what those 5 equations are. T of V1 through T of V5. Then come down here to this matrix, write down all 5 of the equations that you get from this matrix. Again, everything being in terms of the W basis. And what you will find is that the top 5 equations are exactly the same 5 equations as the bottom 5 equations. So, said differently then, these are describing the exact same linear transformation T, just with respect to different bases as promised. Okay, so great blanks to fill in, just make sure that you're kind of seeing how everything fits together. Reminder, this is, we're in section 5.5, but this is arguably a section 5.3 application here. Okay. All righty. Almost missed. There we go. Okay. Okay. So what does this buy for us? We have every rearrangement of blocks can be achieved by reordering basis vectors. Let me say that a little bit differently. When you rearrange blocks, you're just changing from one basis to another basis. Right? You're changing from this V basis to a W basis. It's a change of basis. It's a really simple change of basis where you're actually using the same vectors just in a different order. But it is a change of basis. So rearranging blocks, being as it is a change of basis, rearranging blocks gives you similar, literally similar matrices. It gives you matrices that are conjugate to each other. Okay. All right. Now, why am I making a big deal out of this? Reminder, additional homework problem, going to look a lot like this. Okay. This is what I need to actually be able to state this theorem here. The theorem addresses the potential, the fingers crossed, uniqueness of Jordan form. Wouldn't it be nice to say that every matrix has exactly one Jordan form? That'd be great if it were true, but it's not. And not only is it not true, it's sort of obviously not true. We've actually got an example right here staring us in the face. Right? This, I guess let me just get rid of all this coloring here. We've got here 2 different matrices, 2 different Jordan forms that are representing the same linear transformation, come from the same original matrix, however you want to say it. So this original matrix, clearly, look at this example, obviously has more than one Jordan form. Right? So it's not true to say that Jordan form is unique. What we can say, though, is that, but these Jordan forms are similar to each other. Right? They are clearly similar because they represent T. They represent the same T, just with respect to different bases. So rearrangements are always similarities. With that in mind, here's what I can say. It's not true to say every matrix has one Jordan form, but other than rearrangements, ignoring rearrangements, as previously discussed, obviously those are similarities, so of course. Other than that, every matrix has exactly one Jordan form. So rearrangements are the only way that a matrix can have more than one Jordan form. All right, so that's a big result. Okay, here's an example how you can make sense out of this. Let's look at these two Jordan forms. Basic Jordan block, basic Jordan block. Here, this is the basic Jordan block. These two matrices cannot be similar. They can't be. They aren't rearrangements of each other. According to the above theorem, only rearrangements are the only similarities between Jordan forms. So these are not rearrangements of each other, right? Here we have two Jordan blocks. There we have only one Jordan block. There's no such thing as you can't rearrange two things and turn them into one thing, right? So these are not rearrangements, therefore they're not similar. Therefore, if for example, if this is a Jordan form for whatever matrix you're interested in, then that's not, and vice versa. Okay. All right. So again, big result. Appropriately disclaimed Jordan form is kind of unique up to rearrangements. All right. Okay, so let's talk about eigenvectors. This is a quicker story. Some sort of direct observations. Remember that when we talk about a Jordan form, we're talking about representing some linear transformation with respect to a basis. Don't forget, we call that basis that we use there. We call that a Jordan basis. List of vectors, right? And again, let's just kind of remind ourselves from section 5.3, what do columns tell us in a matrix? Columns are what you get when you take input basis vectors, put them into the transformation, write the output in terms of the output basis. So let's just apply that, what we know, to a Jordan form and see what happens. So here we go. Here we have a basic Jordan block. There's a basic Jordan block. Don't forget the rules for basic Jordan blocks. They're mostly zeros. There's lambda on the diagonals. Whatever's on the diagonal is an eigenvalue. There's ones just above the diagonal. Zeros everywhere else. Okay. So I would like to interpret, given that, let's think about the first column that intersects with that basic Jordan block. What can I learn from that first column? What does that first column tell me? Well, I remind you, columns give you images of basis vectors. So this being, we're going to call it the ith column. This ith column is telling you about the image of the ith basis vector. Now, it's not telling you what that image is with respect to the standard basis. No, it's telling you what that image is with respect to the script V basis, right? It's telling it to you in terms of that output basis. So these numbers here, let's look at what's in this column. It's practically all zeros, right? It's we've got all zeros out here because outside of the basic Jordan blocks, inside of a basic Jordan block, it's all zeros below the diagonal. Above that one diagonal entry, we're outside of the basic Jordan blocks again. It's all zeros except for a single lambda exactly on the diagonal. That lambda in a linear combination of the script V vectors, the output basis vectors, then gives you lambda VI. Right, so that column tells you this equation, and there's a great interpretation of what that equation is saying. It's telling you VI is an eigenvector. Its image is a multiple of itself, so eigenvector. Everybody on board? Straight out of 5.3, we're just applying the ideas of 5.3 to this particular little structure called a basic Jordan block. Okay, neat fact then. When you have a basic Jordan block, that basic Jordan block, they all look the same, pretty much, right? Different eigenvalues. That basic Jordan block, whichever column is the first column to intersect that basic Jordan block, is going to have this property. It's going to be only a diagonal entry, and that means we're only going to get a what you might call diagonal term, and that means that the corresponding basis vector is an eigenvector. Which is really nice. Whereas for any other vector in the list, it just doesn't work. Reminder, here's our basic Jordan block. Let's look now at this column. That column, let's say that's the jth column. That's telling us about the image of Vj. What numbers do I have in that jth column? Well, it's mostly zeros, of course. I have a lambda on the diagonal. So I get lambda Vj. And then I also have, use orange, a 1 just above the diagonal. So I have a 1 just before the lambda in the list of coefficients. Therefore, I have 1 times the previous Jordan basis vector, Vj minus 1. And therefore, I know that for this column, the jth column, T of Vj, not a multiple of Vj. It was trying to be a multiple of Vj, and then this other term crept in there because of that annoying little 1 above the diagonal, and that makes this not an eigenvector. So, not an eigenvector. This breakdown always works. The basis vectors corresponding to the first column of a Jordan block, eigenvector. The basis vectors corresponding to all the other columns, not eigenvectors. All right. So, nice conclusion is then, for every Jordan block, there's exactly one corresponding eigenvector. Right? So, let's see here. So, if you look at a basic Jordan block, there is a corresponding eigenvector, per the rule that we just looked at. Therefore, however many Jordan blocks you have, that is how many eigenvectors you have. I'm sweeping some rigor under the rug here, but plausibility argument, and I claim that this is true. So, the Jordan blocks tell you about which basis vectors are eigenvectors. You can see the examples explicitly, so let's look at the Jordan blocks here. Here's a basic Jordan block right there. Here's another basic Jordan block right there. So for this eigenvalue of 4, there are 2 basic Jordan blocks, and therefore 2 eigenvectors. Furthermore, I can tell you exactly which eigenvectors which Jordan basis vectors are eigenvectors. The first column for that block is the first column, therefore V1. The first column for the next Jordan block is the third column, therefore V3. Those are your 2 eigenvectors. Common mistake, it's not the columns themselves. I'm not saying 4, 0, 0, 0. No, of course not. That's telling 4, 0, 0, 0 is the image of V1 written as a linear combination of the vectors in the V basis. So that's not the vectors themselves, but what that formula is tells you that V1, that we don't know, is an eigenvector. Okay. Same deal here. This is really morally the identical example. Here's a Jordan form. Basic Jordan block. Basic Jordan block. First column. First vector is an eigenvector. First column of the next Jordan block is the third column. Third vector is an eigenvector. You can see what that looks like in the equations. You can see what that looks like in the equations. That first column is that equation. You can see right there it's an eigenvector. Right? The third column is that equation, and again you can see right there that that's an eigenvector. All right. Okay. Real quick, before we run out of time, let me just tell you what we're not going to do about Jordan form in this class. We're not going to prove that every matrix can be put into Jordan form. It's beyond what we can do in this course. We're not going to prove that Jordan form is unique up to rearrangements. It's beyond what we can do in this course. It's we're going to trust that. We're going to use that, but we're not going to prove it. How to find a Jordan basis is surprisingly hard. So we're not going to do that either. Every so often you'll get lucky and we'll be able to find a Jordan basis. I'll show you, with certain free information given, yes, we will. But as a general process, we're not going to discuss how to do that. Okay, this is a good stopping point. See y'all later. Have a good Wednesday afternoon.